coding a Wordle bot. Okay, so for those of you who haven't seen this before, let me just do a recap. So basically, I loaded the list of strings of possible words from the Wordle the Wordle browser. Okay, which is given here. You can actually get your list of words if you go to inspect, and you can get all the list of words here. So today I'll just want to show you the changes that I made since yesterday. So firstly, I added in a more efficient way to like do memorization. Memorization means like store the results of the calculation into like a dictionary or an array. So here we use an array now. Okay, so this guessword function is supposed to take in a guess word and a target word and return the positions of the white, yellow, and green squares, okay, which is like whether it's the same letter, correct position, correct letter, or wrong position, correct letter, or no match at all. So with the memorize function, which is by default true, okay, what we will do is we will just reference. So we have an index dictionary that maps the concatenated word, the guess plus the target word, and then it will return the index, and then the guess word data is just an integer array made up of all the possible like outcomes, and then we can just do in batches of 5 to get the data. So in order to do the memorization function, what I did was I did this thing where I just look. Okay, first we just check whether this pickle file exists. Okay, if it doesn't exist, then we generate the memorization. Okay, we look through all possible starting words and guess words. Okay, do the function with the memorize parameter as false. Okay, then we put all this outcome. I realized putting it as a string, okay, of numbers, of digits, actually is about half the storage size of putting an integer of digits. I guess it's because if you put an integer of digits, there's no upper limit to the width of the integer. So in order to do the compression, it's not as efficient as if I just put the whole thing as one string. So this is what we could do. Okay. Then basically what I did was just to load this. Okay, I could just run the function here. So I already have the guessword data. Let's just load the pickle. So you see it's very fast. So what will happen is our guessword data, okay, will be of length 8. Okay, so what this means, if we take divided by 5, this will be the number of word pairs, and then if we divide it by length words, okay, you can see that it's 12972. So up here is 12972. So it's actually 12972 times 12972 possible pairs of words times 5, because there's 5 outcomes. Okay, and then this whole thing will be stored in the guessword data, which is, if you look at this guessword data, if you look at it, like the first 20 elements is all strings of numbers. Okay, so what we need to do is to then convert it from a string to an integer array. So we run this for a while. This will take a bit of time to run. So we just let it run. So after this, where we get the integer array, okay, then what we'll do next is we'll do an index mapping where we map the words, okay, the guess word and the target word into a dictionary, and then the output will be an index. Okay, I realized that doing this index mapping is better than just doing by finding the index in the words array. Okay, it's because if you put in the dictionary, actually what they will do when you reference the index, they will do a binary search. Okay, so this binary search process is very, very fast. Okay, it's actually like log n timing. Okay, which is like way faster than like if you were to do like finding an index here, which is on, because this is not sorted. So a dictionary implements a binary search for the index, which is a great thing. So we use the dictionary binary search implementation to find out what our index is before we reference the index here. So this is O1 referencing, okay? But this is O log n because of the binary search. So yeah, we're just using the inbuilt thing. So now we already have the list for guessword data. We can see, okay, what is, okay, I guess I'll put here also, like, yeah, put here so that people can actually see for themselves what the guessword data looks like. Okay, so we put here this string of digits. Okay, Um, let me just explain here because I'm gonna release this code, so I want people to understand. We do a dictionary mapping for the starting reference index in guess word data based on the guess word and target word. This is because the inbuilt Python dictionary key referencing uses a binary search, which is, let me say binary search runtime. Binary search is O log n. Yeah, O log n time. Okay, maybe the log n, I'll just put a bracket. Yeah, okay, so that's great. Okay, so the rest is like function to display the game. So why is it so slow? Yeah, okay, so this is the game interface for humans. I mean, you can play this. Yeah, I'm just very lazy to play, so I'm just gonna unjam. Okay, so then we have a few agents. The first agent was the random agent where it just randomly guesses a word. Okay, so we have a game, and then like for example, if the first guess is arise, you can play a few games. Rarer is one of the harder words because you need to guess R. Yeah, then we can evaluate over a few guesses. So I evaluate over the entire set. Okay, but I give it the first word arise. Okay, of course, if I don't give it, it won't be that great. So it managed to solve 82% of the time, which is pretty good for a random agent. And when it solved, it requires about 4.4 guesses. And this is considered quite good because the random agent actually plays it on hard mode in some sense because it just randomly chooses one of the words that are remaining. So where's my random agent? My random agent is here. Yeah, I just choose a one from the words remaining. So it's like hard mode. Okay, I realize if you play the game on hard mode, like for the remaining agents here, it doesn't really work out that well. Okay, it may not be able to guess it well. Okay, but it's slower if I don't do hard mode because I have to give it all the possible words as is possible guess. So this minimize words outcome. What it does is that it minimize if you bin the outcomes for each word. Okay, based on the all the possible target words. Okay, we want to minimize the maximum possible words that could remain after a guess. So let me just show the diagram again. So it's something like this. If we have different possible bins of words like this, we want to make sure that the bin with the highest number is as low as possible. So we take the maximum of all this and we minimize it. So we minimize this bin. So basically, it means that regardless of what the computer can throw at you in like one step, okay, we will cut down the number of words by the most amount. So this is a greedy agent, okay, that does this. Then I also use the three blue one brown. He did the information theory approach, where we minimize entropy. So to minimize entropy is to make the, or rather to maximize entropy. Okay, to maximize entropy, we want to make the probability distribution of all the possible outcomes as flat as possible. A uniform distribution will give the highest entropy. If you're interested in this, is given by Jensen's inequality. There's some proofs for this, quite well known in information theory. So the idea is, let's say if I have my probability distribution as close as possible to like uniform, so this like 2.58, but if I deviate from uniform, then it's 2.52. So this is the entropy function and this entropy agent. You can see like if let's say the game is melts, then we can see that the first word it always chooses is tears. So let's say I give it a harder word like rarer. See how the entropy agent performs. Yeah, not bad. So we let it try to solve 10 games. Okay, because 100 games will take too long. We see how good the agent performs. Okay, so actually I would like to create another agent here. So maybe more advanced agents, three blue, one brown, information theory, minimize variance approach. So this is something that I was thinking of. Okay, so another way to make sure that like the maximum guess is as low as possible is to minimize the variance over here. So if the variance is around the same, is something like similar to minimize maximize the entropy, I think. Yeah, my variance of non-zero bins. See, okay, so the entropy agent solves 100% of the time, about 4, and this also requires about 4, so it's around the same. So okay, I mean we only did it for 10 words. Let's try more words next time. Okay, I mean I will do it off the stream because it will take a super long time. Probably will update this on my blog. Okay, so now let's try the minimize variance approach. So the minimize variance approach is very simple, I think. I'll just go and copy this. This should make I I don't know, I never tried this before, so let's try this. So max variance, let's call it like 1e100 or 1e10. I'm not sure what's the variance, but let's see. Um, get variance of list type some x minus, yeah, mp dot variance. I think I can just do mp dot variance. So maybe let's do this, get variance. I do something like this, get variance. This returns the variance of the. Okay, first we do an mp dot array, okay, and then outcomes equals to outcomes of the index over here, and then return mp dot select only non-zero, because if it's zero, then actually we don't need to do anything, right? Because if it's zero, then the variance will already be like zero. Sorry, if it's zero, it means that those outcomes are should not be considered at all. Okay, we only want to give the variance of the outcomes that still can exist. So mp dot variance outcomes. Hope this works. Okay, so this is get variance. If variance greater than or smaller than max variance, because we want to minimize variance here. Okay, we call this best variance. Best variance equals to variance. Best word equals to word. Yeah, and the same thing, if there's only one, then it should give. Okay, let's try it out. Try this. Okay, my first guess, I should not give it anything. Okay, because we don't know for sure what will the first guess be for the minimize variance agent. So this minimize variance agent will just try to minimize the variance of the possible outcomes in the probability distribution. And I think in so doing, try to make the probability distribution as flat as possible. I mean, I'm not sure myself. I haven't coded this before. Let's see what it gives. Okay, I mean, the entropy agent is not bad. I mean, managed to do quite well. But let's see the minimize variance approach. Okay, give it some time to run. I hope this is correct. Honestly, never coded before. I hope the best variance is enough. Okay, but given that there's only 81 times 3, which is like 243 outcomes, I don't think the variance can get very high, like 243. Yeah, I mean, the variance of, okay, maybe I should have tested out the variance function. Yeah, you just gotta wait a while for this to be coded out. Okay, meanwhile, I'll just create another function called use an agent to play the game. Play the game online. Okay, so this is the last part I'm gonna code. So let's see. This is my game. I'm gonna do something like this. Okay, but instead of you giving the guess, this will return you the guess. Okay, for each state. What you need to do is just key in what are the words and the output distribution. So we call this AI helper. Yeah. So this one is basically oh, what's the first word? Test. Okay, so the minimize variance agent apparently uses test as well. So we can try first guess equals to test. Seems like test is a very good starting word. I mean, I guess it's as ST and ARE also. So you have this. Okay, but there's something wrong here. Like once it reaches here, it somehow doesn't seem to be able to get the right word. I mean, the variance doesn't really work out. Okay, but before that, let me just try this out here. Like get variance. Okay, we try like 3, 4, 5. See what's the output. Okay, if I put like multiple zeros, okay, good. Now 5 here, 0.687. So let's say if we have output of uniform distribution, oh, the variance is 0. Mm, that won't do, that won't do. I need to, because if the variance is 0, then a lot of words will have variance 0. Okay, uh, maybe what I need to do is I need to say that, mm, yeah, yeah, I can't be having all zeros. I need to, maybe I need to add the mean, but if I add the mean, then it will be the same for all cases. Maybe I need the mean of the, yeah, I guess if I do minimize variance approach, I cannot, I will get a 0 for this, which is great. But then for the all 0 case as well, like that, I will also get 0 because there's only one output here. Again, I want to avoid something like this. So I need to make sure that my minimum sum of the, yeah, basically in order to get the best output for this, okay, the variance needs to be low. Okay, but with only one output like that, the variance will tend to be high. Okay, unless I don't put this here. Let's see. So this will be 2.2. So if I count the 0 elements as well, what will happen? Yeah, actually this is better. So this will like spread it. I should count the 0 elements as well. Yeah, so that if there's only there's one pick, this will be very drastic. Yeah, And if let's say everything is like that, okay, my only worry is that there can be a lot of zeros. 2, 4, 2, 2. No, this is not bad. 2, 3. Yeah, maybe I should count the zeros as well. Yeah, I don't think mean is actually a good way. I mean, I could try it, but I think the variance will be good. So if we minimize variance, we try to get it as flat as possible. So yeah, okay, let's try this again. Okay, let's just see if let's say we have 2, 4, 3. Let's say we have 2, 4, 3, and then we have lots of zeros. Okay, looks good. So let's say we have 1, 1, 0.08. Okay, so I think I have to add in the we just minimize the variance directly. Okay, let's see how this works. Oh, that's fast. Oh, because the first guess was test. So let's remove the first guess, and we see what the variance agent will give us. Okay, so if we minimize the variance, I mean, in some sense, I guess variance is related to entropy. If you minimize the variance, your entropy will be higher. Okay, so they are just approaching, this is from a probability approach. This one is just simply from a distribution approach. And we see whether this minimized variance agent is competitive enough. Of course, I mean, in the future, I might try out some reinforcement learning stuff. We can do DQN, actor critic, on this using state space and then predict the guess. Okay, I mean, given that the random agent has already given like us 82% solve rate for all the words, I would say that any agent needs to fare above like 90%. Okay, if not, it will be like worse than random. Okay, so random agent for Wordle. So if you just throw a dice, okay, and then you just guess any word, and then you eliminate all the possibilities based on the total guesses. Okay, you should be able to solve the Wordle game like 80% of the time, at least. Okay, because there's a random solver. Okay, with basically no heuristics. Okay, but I mean, for humans, we don't really have the word list with us, so we go by like more common occurrences. Actually, this is the harder version of the game because it has all 12,000 words as possible guesses. Okay, so let's see our. Okay, we need to give it some time. Okay, let's code the AI helper function so I can solve like today's Wordle with this. Okay, just to test out the agent. Okay, so the agent here. Okay, don't need to change. Okay, actually, all this don't need to change. Returns. Okay, returns the next guess. Actually, I don't need to return anything. Okay, so we have all this. Okay, uh, okay. So I don't need to have a target word because the target word will be given by. Yeah, I don't even need to do the guess word function. Okay, get the get the get the outcomes. Okay, so from the online server. So we do input, key in your outcomes. Maybe what we can do is we can print. Okay, So this one, the display will always be true because we want to show this. Okay, prints. Okay, the agent suggests to use suggest the word, and then we can just put guess. Key in the guess outcomes. The server 0 for white, 1 for in a string of 5 digits. 0 for white, 1 for yellow, 2 for green. Okay, so maybe we just take this as okay. So I need to check whether these outcomes are correct. This is a bit of brute force. That's fine. I mean, we only do it once. Invalid input. Okay, like that. Okay, then this will be our outcome. Outcome will be the list int list map int outcome. When we map convert this to an integer array. Okay, like that. Okay, list guess list outcome. Find out the words that are possible still in the list. Okay, so we still need to do a guess word here. Okay, in order to just check what are the possible words remaining. Okay, then we will display. Okay, then here else we just print out the bot was the agent was unable to help you solve it. Okay, yep. So this one you just have to follow whatever the agent tells you to input, and then we will. Okay, we try this. Okay, so turns out that the first guess is less. Okay, so let's see. Less. So I don't think less is that great for variance. Okay. Okay, let's try fuzzy. No, not too bad. Okay, let's try out this agent. Okay, over all. So this is the minimize variance agent. Let's try this out over like 10 games maybe. Minimize variance agent. Let's see how I typed it out for the first. Minimize variance agent. Okay, requires this. Okay, so okay, let's see for 10 games. Okay, since the first guess was always going to be always going to be less. Okay, I mean this is only a one step look ahead. Okay, let's see. Given like maybe the first 10 words. what's the average number of guesses it needs. Okay, so a more fair gauge will be if we do this for like over all the length of the words. So I'll run that later, and I'll update my blog uh, what's the outcome for this agent. So looks like the entropy agent is doing quite good. Actually, this minimize worst outcome agent is not bad as well. Yeah. So let's see. Oh, 4.1 guesses is slightly inferior to entropy agent. So the minimized variant approach is not as great. Maybe we could inculcate not just minimizing the variance, but also like getting a low minimum here. Yeah. So not just yeah. I mean, it could be a hybrid of like this approach as well, where we take the maximum outcome. Yeah. So there are various strategies that could be tried. Okay. Information theory approach will give you the best outcome on average. Okay, but it may be bad. I mean, if you play against like Absurdo, it might give you a bad outcome. Okay, because the Absurdo will make your worst case come true. So this directly counters Absurdo. This minimizes the worst case. Okay, but minimize variance, I'm not sure where it stands actually. Yeah, I'm thinking maybe minimize variance can be combined with maybe minimize variance and minimize maximum. Okay, why not? Let's code it out. Okay, let's code it out. Okay, so like minimize variance and what I call my top agent, minimize variance and minimize worst outcome agent. I mean, that's the benefit of having coding software, right? We can code it out. So we have all this stuff here already. Okay, minimize variance, get entropy. Okay, this minimize worst outcome. Okay, so what we'll do is we'll just copy this code here. So actually, ideally, I would like to make my agent like a class. Okay, so that we can like not have this function outside. But I'm a bit lazy to do that. And I mean, given that this is not the main thing that I want to focus on, I want to do some like reinforcement learning stuff, which perhaps can do better than this for by the information theory approach. I think using some form of a Markov decision process and modeling the state and the actions, you should be able to get about 3.5, 3.6. Okay, I think it's possible because honestly, there isn't really much. There's only 10, 12,000 words to guess, and the random agent already did like 80% accuracy. I mean, 80% solve rate for all the words, 82% solve rate. So I think it should be fine to use a DQN because even you do a random, like even you do an epsilon greedy deep Q network, um, the chance of you having a solve will be quite high, and hence you will be able to update your value states quite well. I mean, I don't know, I never tried it, but I'm quite keen to try it. Maybe I'll do it live on the next stream or something. Yeah, but today's stream I focus on doing probability based methods. Variance is technically not a probability based method, but it's very similar because minimized variance would also lead to somewhat uh, flatter distributions. Okay, so let's try this. Okay, we have the variance. Okay, plus max of guess list, minimize variance, and worst outcome agent. So we do have a factor that we can actually, I guess we could have a weighing factor here. Yeah. For now, we just make them equal. Okay. Let's see. Display a single game. Okay. Ta-da! Okay. And the agent is minimize variance and worst outcome agent. Wait a minute. I shouldn't give my first guess. I want to see what's the first guess that it comes up with. Okay. Then after that, we try for 10 words and we see how this agent fares. Okay. Oh, I realized something. This first guess should be less, not test. Okay, so I'll need to rerun this cell again later. Maybe I'll run it offline because I got to go soon. I hope that I can at least solve like today's Wordle using one of the agents. Yeah, I quite like. Maybe I'll try the minimize words outcome agent, or maybe we could try the information theory. I don't know. Both are fine to me. Yeah. Okay, so we try one. Okay, I just want to see what's the first guess, and then we can try to play 10 games. Okay, so this AI helper is almost done. So what we need to do is just to run it. AI helper agent equals to information. What do I call it? Entropy agent, right? Entropy agent. Yeah, entropy agent. Entropy agent. Okay. And we already know its first guess actually. Yeah. Here, maybe let's just let it come out with the first guess by itself. Max guesses equals to 6. Okay, like that will do. I think this will be good enough. Okay, it's taking a while to come out with the first guess. I'm not too sure why. Okay, it should be quite straightforward, isn't it? Like, okay, so we are waiting for the minimize variance and worst outcome agent. Not too sure why it takes so long to. Oh, less. Okay, looks like their first guess is less also. Is less that great? I don't know. Okay, maybe we just try solving this for 10 times and see how this works. I'm personally more of a fan of tests. Although I use the word arise for my starting word. But entropy agent gives me test. Test is fine as well. Yeah, test got ST and R. But less L. Are there a lot of L's in the English words? I'm not sure. Yeah. Okay, let's try the AI helper function. Then we try to solve this. Okay. Um, Today's Wordle, and we see like whether or not the information theory agent is about 4.2. So it looks like the best case, like minimize variance 4.1. Okay, the entropy agent is about 4. The minimize versus outcome is 4. So actually minimize versus outcome is actually not bad as well. Okay, but let's try using the entropy agent, okay, to play the online game. Okay, let's just run this. Okay, I forgot to put a close bracket. Okay, we probably need to do something here. If outcome should break, yeah, break out of loop if solved, because we don't know the guess. Okay, so the target word part, I'll take away this. And it's like that. Okay, so we wait for the agent to tell us the best word, which I think should be test, based on what we got from the earlier part. Okay, so I believe most of the time when people put these bots online, the first word is already predetermined. So it cuts down a lot of the processing time because it's always the first word that's the toughest. 12,900 possibilities times 12,900. It's close to a billion or 12,000. Let's see, four zeros plus four zeros, eight zeros. Eight zeros is three hundred million. It's around 100 million. It's almost a billion. Okay, so if we already give it the first guess, which we could because we could put the first guess here. Yeah, we could put the first guess here. Okay, we can make the first guess, like what do you call this? Tests, because the entropy agent will always give us tests. Okay, but right now let's just let the entropy agent run through the entire list of words over here. Okay, and come up with the first guess. So I believe the first guess here should be tests. Okay, later on I'll just let the agent do their first guess. Yeah, no, because it's taking a bit too long to do it. I prefer if the first guess is given to them so that it will be faster. Let me just delete all this. I hope I didn't make an error in my code here. Yeah, it's still doing. Maybe I should give it the first guess to help it speed up. Yeah, yeah. Okay, I think it's okay. Yep, he suggests the word test, but where's my input prompt? Yes, where's my input prompt? Where's the input prompt? Oh, okay. Looks like I cannot support input prompts in a function like this. So what I need to do is I need to do it like that. Like here, agent equals to entropy agent, max guesses equals to 6, display equals to true, first guess equals to test. Define your parameters here. Okay, start of box. Okay, so we do it here like that. Okay, so I guess all this uh, find your agent here. Okay, where's my input prompt? Where's my input prompt? Raw input was called, but this front end does not support input requests. Okay, that's weird because I think it should support based on what I did for the earlier game here for humans. See, we can actually do this. See, you can key in here. Okay, we just end the game. I just like ending this. Okay, so it does look like we can actually do the input here. I'm not too sure why it doesn't allow me to do it here. So oh, actually, did I set my clear output to be true all the time? Oh, no wonder it takes so long for the game. Because this should only be done if okay. So this may be why the agent takes so long to work. Because like this wait is quite annoying. Yeah, they're much faster now without this. Yeah, I should have put this clear output equals true. Okay, let's see. Entropy agent, first guess. Okay, okay, good. So what I need to do is I need to put it here. Okay, so let's key in the word test. Okay, so this is a bad one. 00001. Soily. The agent suggests soily. Okay. 21010. Fluke. What is fluke? 02200. CC. Okay, this doesn't look great actually. There's two possible words remaining. He suggests the word CC. Okay, but you know that there's L and O here already. So I'm not too sure why they still suggest this word. Okay, there might be an error in my code. Okay, because uh, it should be SLO something something. SLOPE slope. No, cannot SL. Not sure why they suggest this word CC, but you know what? Let's just try it out. Oh, there's two S. No wonder he did this. I guess to just make sure. Two, but I mean you should already know, right? Slosh. I never heard of this word before. Okay, so the bot works. Okay, wow, this word is difficult. What is slosh? Oh, it's the liquid, sloshing liquid. Okay, let's try absurdo. Okay, this one is wrong. Okay, it should be okay. So we can do this. I don't quite like the input being cleared immediately after we do this. Okay, after we key in this, I want the agent to actually like suggest the word first, then we clear the input. So maybe something like this, such as the word gas. Yeah, something like that. Yes. So let's try test. Okay, so Absado gave 0 for everything. We see what the entropy agent gives us for the guess. Colin. Okay, so okay, I don't quite like the way it's displayed again. Okay, so there's some issue now. Okay, so let's not put it here. Let's put it here. So the next word will be colon for Absado. So let's see. Okay, I didn't clear input. Oh, okay. Yeah, probably should just put if display clear, something like this. 02000. Boody. Oh, nice. Oh, no wonder there's 6 possible words remaining. Right? Why? Okay, let's key in this again. 00000. Feel a little slow. Okay, colon. We do colon was 02000. After that will be Budi, which is 02222. After that is dwarf, which is 10000. Hump 00000. Budi. Yes, okay, that's great. So let's use instead the agent called the um, minimize worst outcome agents against Absado, and we see how it works. And the word is Sarai. Sarai. Okay, let's try again. Let's see what the bot suggests me to key in. Phony 00102. MULCT. Oh, what word is that? Dodge. Blush. Bobby. Okay, so it looks like both seem to work out pretty similarly. Okay, let's try the minimize variance and worst outcome agent. Okay, and the word that we want to give it starting word is less. Okay, let's try again. Absolute. So it's about 6 for the information theory method and the minimize versus outcome agent. So yeah, information theory is pretty competitive. So let's see. Absado was 0 0 0 0 0. And let's see what's the outcome for this. Bions. Oh man, Absado likes to do this. Pick me. Chef. I always wonder why they pick double letters. I mean, shouldn't you pick evade? Yeah, so there's two words. Of course, Absado were fuzzy. Okay, so this was the minimize variance and worst outcome. Let's try the minimize variance. Okay, it looks like everything is about 6 for Absado. Let's try the minimize variance approach. Absado is not bad in terms of like making our agents work for it. Okay, first guess is less. And let us see. So again, we're gonna start with less. Again, we're gonna get 0 0 0 0 0. And now let's see what the minimize variance agent will give us. Okay, in terms of like what is the next word to guess. Tonic. So the second word is a different word already compared to 0 2 0 0 0. Booty. Looks like they like booty a lot. Not sure why. This is similar to the actually this minimize variance is similar in performance to now it's dwarves instead of dwarfs. Okay, 1 0 2 0 0. Omega. Goody. Okay, so using this Wordle bots, okay, I've shown that like all the approaches here actually have similar performance to the. Okay, let me just type. Let me just type it here. All four bots have similar. All four agents take 6 tries to solve Absado. Okay, so yeah, I guess Absado, if you want to do it properly, you need to probably do a like 1 or 2 step look ahead because Absado will definitely play the worst possible. You already know its game plan. You already know its game plan. Okay, so I guess one thing is basically we try multiple guesses, and then you look ahead at what the guess would be. You try to um, go back down. So if you go downwards multiple depths of your search tree, and then you go back upwards again, and you try to find the least of moves to minimize the least of guesses to minimize your number of moves or number of guesses. So in order to win against Absado, the best possible move is 4. Okay, in order to do that, you have to do some look ahead tree searching. Okay, but I think this is not bad. I mean, it goes to show that actually you don't need information theory. Actually, I mean, I myself a bit. I'm trying to think of approaches that can do away with probabilities because probabilities tend to be intractable at high dimensions. So, like the VicRec paper that Lacun did, it uses variance. I'm trying to see whether there's other approaches variance is a nice one, it's a statistical approach. I'm trying to see whether there's other approaches that can actually help us solve this problem, okay? But not like needing too much like probability data. So that's something I'm trying to work on. But yeah, so that's the end for today's stream on Wordle. Okay, next up, probably we'll do something on reinforcement learning to solve this problem that will incorporate some form of look ahead using a Markov decision process to solve this. So yep, catch you around. Okay, and see ya. Oh yeah, just pause here for a minute. For the viewers, do you have any questions you want to ask so far for the bot? I will be releasing this notebook on my GitHub. Okay, so yeah, my GitHub link is on the Twitch links there as well. So yeah, if no other questions, I think yeah, it was fun doing this. So I myself actually don't like to use a bot to solve my own Wordle puzzles because I think I'm smart enough to do it without the bot. But I mean, the bot is just a fun exercise. Okay, and next up, the DQN or the actor critic model. I saw someone in Weights and Bias do it, so it piqued my interest. So I decided to do it myself. The best way to gain experience is to code it out yourself. Yeah, and I got motivated to do this bot from three blue one brown because three blue one brown did this information theory method. Okay, and actually it worked out not bad. Okay, although I would say minimize worst outcome can perform that quite well as well if you talk about one step greedy search. Same thing for variance is the same thing, and this also around the same. So I mean I don't see much difference in all methods. This one takes a bit longer actually. This one takes a bit longer. This one is not bad. Yeah, this one is good also. Yeah, so I think I like the first guess, Sarai, because I use Arise as well. So I'll go and run this on all possible ones and we see what's the performance of all these approaches. And yeah, see you around. Bye.